everyone. Welcome to 2021 Virtual TechCon. My name is Sarnaha Chowdhury and I'm a PhD student in the Department of Electrical and Computer Engineering at Purdue University. Today I'll be talking about laser-induced plasmonic color printing on semicontinuous metal films. A brief overview of the organization of this presentation. Initially, I'll be discussing about what are semicontinuous metal films. Then we will be talking about how we can achieve such films. And then a new technique that we have proposed is how we can modify those metal films to change the optical spectra. And as a result, how we can see changes in the color if we want. The entire goal of this presentation is to generate stable colors using the semicontinuous metal films, and that issue of stability is also being discussed in this presentation. And finally, we'll be talking about some artistic designs obtained using the semicontinuous metal films. Now, what are semicontinuous metal films? Now, imagine you have a layer, a substrate, and at the very initial deposition of metal layer, we have some random nanoparticles, metal nanoparticles being dispersed on top of substrate. If we increase the deposition, gradually all of these nanoparticles are going to merge and combine together, and that at a certain point, you will be able to have a continuous metal path from one end to another. The stage where you can see this transition from dielectric to a metal layer is known as the percolation threshold. Now, we are interested in this region just before the percolation threshold, where we have like a high density of metal nanoparticles being dispersed. And as you can see this from this figure, that these nanoparticles are of different sizes and shapes. These densely populated metal nanoparticles right before the percolation threshold is what we are calling semicontinuous metal films. Now, one of the features of the semicontinuous metal films is that based on this morphology of those nanoparticles, we can different parts of the spectrum can be absorbed, reflected, or transmitted. These nanoparticles, they can harness electromagnetic energy like numerous folds compared to the light illumination, and as a result, we can utilize this concentrated electromagnetic energy, which are known as hotspots, for our further benefit of modification of optical spectra. Now, how do we achieve that? If you think in this graph as this red dots as metal nanoparticles, what happens is that around those metal nanoparticles, they absorb light. And you can see that they have a broad absorption spectra, and this absorption occurs because of the different sizes and shapes of the metal nanoparticles. Now, if you have a very high energy density laser irradiation, then what happens is that induces thermal photomodification. Basically, because of a high energy density laser modification, you will be able to change the size and shape of those metal nanoparticles, and as a result, you can change the optical spectra, because as I've discussed that based on the size and shapes of the metal nanoparticles, different parts of the spectra is being reflected, absorbed, and transmitted. And if you can change the size and the morphology of those nanoparticles, you will be able to change the optical spectrum. This is what is of our benefit at this point, and we are going to utilize this method to generate different colors that are based on reflection mode. Hence, as we have discussed here, that we are proposing a new method, which is we have semicontinuous metal films, which are randomly dispersed nanoparticles, and we use this photomodification of the semicontinuous metal films to create broad distribution of optical spectra, and we can modify that. There are other methods which are also used currently, where you have metamaterials fabricated by e-beam writing, but this is an expensive method. What we are suggesting is lithography free, because we're not using e-beam writing, we're just using a simple deposition method. Then these structures are going to be very stable, as we are going to discuss in the upcoming slides. And of course, it's environment friendly because we are not using any artificial harmful dye here. So like finally, if I can describe the structures and the steps that we are going to do, we have these nanoparticles, and then we have high local fields around those nanoparticles, where if we have like a very upon light illumination, and we can use those structures and modify them with a laser so that we can change the size and shapes of those metal nanoparticles. Now, the structure that we are proposing is a very simple glass layer, where we have a silver layer on top of it with a titanium addition layer. The silver layer is used as a mirror to see the colors in a reflection mode, and then we have silica, and then on top of it we have metal nanoparticles being dispersed. This structure is basically in order to utilize the gap plasmon modes. Now, as we know that silver degrades over time, it oxidizes very easily. That's why we need a protective layer on top of it in order to ensure that those metal nanoparticles are stable. Now, once we overcoat it with 30 nanometer silica layer, we see that there is a broadening of spectrum here. As you can see, the absorption shifts and broadens, as well as the structures are more stable. So hence we have this proposed structure that we are going to use in order to utilize that has a part of gap plasmon modes, as well as the silver nanoparticles, which is the semi-continuous metal films, in order to have a further modification, photo modification later on. Now, before we proceed to the laser modification, we need to at first identify what is the thickness of those metal nanoparticles that is going to give us the best absorption or the highest absorption in order to modify it later with the laser. Now, what we did is a study based on gradually varying the silver thickness and see which one gives us the most absorption, and then we do an overcoating on top of them to see like how the spectra, the reflective spectra, changes here. As you can see here that the 7 nanometer using at a very low thickness of metal layer, we see that the 7 nanometer or 5 nanometer, they are being absorbed and reflected, and when upon coating it with a 30 nanometer silica layer, we see the best combination in order to get like a wide spectra of absorption in order to modify our films. Our laser setup is based on what we use is an 800 nanometer femtosecond laser, where we have our sample being placed in an XYZ motorized stage, and then which is capable of raster scanning, and then we have a focused laser beam on top of it. We have a MATLAB code that changes the stage motion in order to obtain different colors. Now, colors or like the optical spectra or the modification of our semi-continuous metal films can be achieved by changing the power or energy density of the laser, the scanning speed, and the line spacing. So we have a number of parameters we can play with in order to get like different colors or different parts of the optical spectrum being reflected. Now, as we have said that the 7 nanometer silver with the 30 nanometer silica coating gives us the best combination of results, and here you can see that upon increasing the energy density, what we can see is a wide variety of colors being generated. Here we change the energy density instead and keeping the line spacing and the scanning speed fixed. And you see that the initial color was blue, and then as we gradually increase our energy density, we can see a gradual change in the optical spectra, and the corresponding color, reflected color, also changes. Here you can see in the corresponding CI color map that we have a wide range. Just using one substrate or one film, we can get all these colors. Now, one of the issues with silica overcoating layer of on 7 nanometer silver film was that when we checked it, like after months, we saw that the silica overcoating layer was not enough to protect our silver layer, and they gradually degraded over time. So we decided to go with a conformal coating layer that is capable of locking those metal nanoparticles, and we coated our silver layer, our 7 nanometer silver metal nanoparticles with 5 nanometer of alumina. And here, as you can see, we were able to get the same reflected spectra after months, and we can summarize this as like the silica layer. Compared to silica layer, our thin layer of alumina layer is more stable, which is an additional benefit of making this structure thinner than it was before. And because of this conformal coating, we were able to also do the SEM characterization that was helpful for simulations later on. Hence, after obtaining a stable structure, we try to modify the structures using a laser, and as you can see here, we can again get a wide variety of colors by changing the energy density, and the structures are also very stable. We have, as you can also see in the corresponding CI color map, that it generates a very wide range of colors upon changing the reflectance spectra by shining laser on top of it. Hence, we can conclude that by varying the silver thickness, at first what we tried is we changed the silver thickness layer to obtain an optimum layer that is going to give us the most absorption to modify. And then we used a high energy density laser, the second laser, that by changing the energy density, we were able to modify those metal nanoparticles. We were able to change the shape and the morphology of those metal nanoparticles. As a result, this gave us a variation in the optical spectra in the reflected mode, in the reflection mode, and this correspondingly changed the color that has been generated. We were able to print different images using a MATLAB coded interface with the XYZ stage. And here you can see we tried different designs. All of these designs were part of an exhibition at Purdue, that's like Conference of the Future, Purdue 2050 Conference of the Future, where we kind of showed how engineering can be transcendent into aesthetics. I would like to thank my team for helping me with the funding, and of course we have different collaborators around the world who helped us achieve this work. Thank you everyone, and please reach out to me for any questions.